Yeah, so we're not halting anything. If I don't halt, what's the problem here?
We outputted the,
Yeah, we have to run this program in our head. So when x is true, I'm going to assign y to be high, but y will be false. And this branch won't be taken. So z will be true, low. Output is fine. The pointer won't stop. When y is false, when x is false, this branch won't be taken. This branch will not be taken. And then, because y initially is true, I'm going to set this to false, but y is also low, so z ends up still being low, but set to false. Now I'm output false. So the output of this z is the same value as x. I'm leaking x. Even though I'm taking the branches, nothing bad happening here. Yes, this is like a classic example for implicit leaks through tainting. Like people are like, oh, taint monitor is great, then you always have to think about this example. Very weird. The problem is branch not taken. The branch is taken is taken care of, but you can always leak information through the branch that's not taken. That's what this program is taking advantage of. Okay. All right, so now I want to do this gradual typing in the next 10 minutes. So again, gradual typing is like this idea where if you ask programs to write types, maybe they will never use it. So therefore, we're going to do this dynamically. We're going to allow programmers to use question mark or star, depending on different paper, do it differently. Basically saying that, hey, I don't know what type it is, deal with it. So now I have a type system. If the program actually marks precise types, I'm going to check it. But whenever a program tells me star, the type checker does very little. It just lets it go. So in the majority of dynamic or gradual typing system, if you give it untyped lambda calculus, the static type checker won't say a thing. It will let it go. Right? However, I have runtime monitor. As the program runs, as I'm seeing operations being done, I'm refining the types. I will reject program at runtime. So Ron Garcia had this really nice paper a while ago at POPL, where basically the simple way to characterize this is that what the gradual typing runtime monitor is doing is actually make sure the type is preserved. And when it sees there's no path to preserve the type, it aborts. That's kind of the first summary of what the typical system is actually doing. Right? Now, in our setting, so in the general setting, obviously you care about function, care about sum, care about parametric types, so on and so forth. But when you introduce parametric types, things gets crazy. But for us, it's all simpler. I just care about labels. Right? I'm just assuming, let's say that the other types have been dealt with, but the programmer doesn't want to mark the secret or not in certain parts of the program. Right? For the ones that's important, I would assume them to mark them. But for intermediary variables, things in the middle, I don't care. They're just not going to give me a label, so I'm going to just assume they're going to have a question mark. So for the static part, if x and y both have types and both have labels, my type checker is going to check it. If one of them is star, I'm going to let it go. I'm not going to check it. So the way to do this is when I check the lower than label, the typical one is I allow this relation if there are letters in the right order. I also additionally allow a question mark to be less equal to anything, right? Except the special case is top and bottom, but yeah, generically, when you say the question mark, the rule is actually fairly loose. So in terms of interpretation of question mark at runtime, when you tell me question mark for me to stop back program. So for example, I can take a secret, cast it to the question mark, then try to assign it to low. That's bad, right? The static type checking won't do anything. By runtime, I need to know that's bad. So at the runtime, I can keep track this question mark's interpretations. I'm refining what I know about this question mark. When I know nothing, it's all possible labels on the letters. Gradually, I'm refining the range that the label can live in. So the interpretation is a pair. There's a low bounds on the label, there's a high bounds on the label. Right? So as I'm doing this, you can imagine this region gets smaller and smaller. Right? So that's at the high level. So it's already in real semantic rules. I'm going to give you examples. So here I have a monitor. I have this branching thing here. I already know x is high. If I know x is high, the range low and high are exactly the same. Right? So here, basically all the values now have a range in front of it. For concrete label, the low and high are the same. Now y, I don't know, I have two parameters, y is question mark, so it can be either low or high. Right? So when I do this assignment, what I'll do is, because I'm, not assignment. When I first do branching, when I do branching, I'll just pile up the PC, so now the top is actually a high context, nothing else changes. And now I'm going to do this assignment y. So when I evaluate this assignment, because I'm under high context, I'm going to refine y's label to be high. Because it can only safely happen when y's label is high. So that's one way to do deal with dynamic or unknown security labels. Right? This reminds us of tainting, right? So that's actually one of the problems. This is like easy way to refine it, but this is actually slightly wrong. So what's the problem is that, this is not exactly a problem yet, but so let's say that, keep that as an example for us to how to do refinements. I'm going to introduce a guarantee that's actually hard to satisfy for some of the information flow gradual type systems. So this guarantee called gradual guarantees. Obviously not every gradual typing system satisfies this, but this is a desired property, a good gradual type system should satisfy. So the idea here is that, let's focus on the dynamic one. The idea is that if I have a program that can run with no problem with the programmer giving me all the labels, now if the programmer got lazy, didn't annotate some of the labels, I shouldn't terminate that program. So that's what this dynamic gradual guarantee means. The static one talking about type checking, right? So we're thinking about what's more precise, what's less precise. So this one, in this program, in these two programs, the left one more precise, I can give you all the labels. The right one less precise because now y doesn't have a label, right? So basically, if I run this program runs fine. If I run that program, my runtime shouldn't somehow stop that program because there's one version of it can run fine. My system should be more permissive. So that's what the gradual guarantee is talking about. Okay, so keep that. Actually, any questions before I swing around about the gradual guarantee? It seems to make sense, right? If I allow the programmer to use question mark, I shouldn't penalize them for using it. Okay, so I give you one version of how to implement gradual implementable typing. I already hinted at it looked like a tainting. It turns out to be true in that if I use that system to type check this program, where again the same program except I make y question mark. I just say, hey, I don't know what's y's label. This end up actually leaking information. So that gradual system is not secure. So now I have to fix it, right? So one way to fix it, how do I fix it, right? The problem is this untaken branch has been an issue, right? So in Ron's paper, what they decided the problem is that when I do this assignment of y, y has question mark, so therefore y's interpretation can be low or high, but that means that low is a possibility, right? So if I have any branch that's in high, I should decide that that's a bad thing, because it's possible that y is low. This assignment shouldn't happen. So I'm going to disallow this. So here, at this assignment, the PC, I'm checking whether it's lower than the interpretation of the label. The interpretation of the question mark is the range of low and high. If my PC is high, because I have one element, this relation doesn't hold. That's the reason why I'm going to reject that program. So that's what the decision Ron's paper took, essentially. Seems sensible. I want to turn the program early. Yeah.
So essentially, the question mark, you just take the lowest of what the options are. Treat it as if it's the lowest of the options. Yes, exactly. So now comes the problem of this simplified program. I have x, y, but basically throw out some other programs. So here I'm going to assign y to false and output y to high. This will be rejected because inside here, this y can be question mark, x is high. It's possible there's a danger, I'm going to throw away this program. But if the programmer had given me a type here, this program would run fine, right? So it will be rejected by the runtime. So the decision to reject program for security end up violating the dynamic gradual guarantee of the type system. Right? That's one tension that they found out.
Yeah, so I had a conversation with Ron while he was at CMU a couple of years ago. I think there's a better solution. I think if your monitor reacts too conservatively, you're going to surround with programs. So instead, we have a couple different papers on this, but the one that connect to monitoring very tightly is this hybrid approach. What we realize is that when you have a branch like this, you need to take care of untaken branches. You can't just say, hey, when this branch is taken, I'm going to do some action, right? So this is what we call hybrid approach. Actually, in the information flow monitor field, people have done this independently in the monitoring field. So what I'll do is, I do require more effort in that for every branch, I'm going to ask the programmer to tell me what are all the variables could have been accessed on either branch. Right? So here I have one y assigned to y, therefore in this branch, I'm going to mark this y being the variable could be written if the branch is taken or not taken. Right? If this y is in the else branch, being written in the else branch, it will also be in this set. So then what I'll do is, I will, when I go to the branching statement, if the PC is high, I will look at this set variable y. I'm going to upgrade all the labels that could possibly be written ahead of time before I even start writing to the variable. Right? So this is called a hybrid approach. You look ahead. You know ahead of time. It doesn't matter if the branch is taken or not. You know that these are variables will be written, and I'll deal with that here. When you do that, we can reject the program appropriately, and also we actually have value guarantee in this specific setting. Right? So this is one kind of connection between type system and runtime monitoring. I'm not saying like my monitor is the monitor or wrong monitor is the monitor. It's more of in general. It's not the case that the runtime monitor and type system are completely separate. If you have this gradual typing type of system, you do have to take care of the runtime. You also have to take care of static semantics. The choice of runtime is different, right? The same as initially I talked about taping and strict is different. Our design monitor is different. The other papers now come out now. They took yet another different choice, different set of trade-offs, essentially. Any question about this? Yeah. Yeah. Well, you guys figure it out.
That static, like you say that there could be a static analysis to determine, like for the branch. Is that like possible for it to be complete, or is that going to be like?
Well, if you write in Rust, I'll tell you what that is, right? Okay. If you write in C Rust, yeah, for sure. But if you write in mostly C with pointer casting, that probably I can over-approximate. Yes, I can always over-approximate.
But Rust is already statically typed, so I guess like.
Not the information flow type though.
Okay.
But
okay.
Rust type checker will tell me what are the variables.
Yeah.
For sure. I know ownership and stuff. Yeah.
I could also do my question at the end. It's kind of more general.
Yeah, how realistic it is, right? So if you have good language, yeah, this is very possible. If you have bad language, I can do over-approximation. When there's C analysis, there's abstract interpretation for C, right? If you write in reasonable program, like pharma C, would actually give you the domain, over-approximate domain, I can actually use that. But yeah, bad program. I should talk to John Reynolds. He was telling the program verification is, in general, a partial correctness problem. If the program write bad program, they don't deserve to be analyzed. So I completely agree with that. Absolutely, 100%. Maybe not to throw more concept at you, but I know some of you are doing verification here. So in information flow world, this is one of the ideas that's really interesting is that I can do verification using self-composition. This is like, I think this can be done for input-output system, but this is easier to explain. Just think about beginning and ending memory. So again, if you have a program, you have low input, high input, and low output, high output. So this is like L and low, L and H in and out. So that's the four sets, the four things I care about. So what self-composition is saying is that when I write this program, so I'm marking all the free variable here, I can concatenate the program with itself, but rename all the variables to be prime. And then this is your assume. The precondition is that all the low inputs are the same. This is assert. This is, the top is assume, the next one is assert. The post condition you need to check is that in the end, low outputs are the same. Right? This is non-difference, just coded in your verification language. It makes sense, right? So this is the same as for all inputs, low inputs are the same. In the end, the outputs should be the same. So this is saying that I'm similar to myself. I didn't have to do the proper variable renaming. Right, so you can do this verification. Even though logical relation is also a hint at when you interpret information flow types, it's a pair of things. Right? So there also work in that domain as well. Okay, so I ran out of time, but I do want to just say one more thing that actually I've been doing some work in there. I want to talk about the other side of information flow security. I've been talking about, these are bad programs, we want to make it secure, here's how we do this. So the other side of this, when you have negation of a property, what you have is vulnerability. So it turns out that what I've done here, I can also use it for vulnerability detection. There are actually quite a bit of vulnerability caused by information flow violations. Obviously, secrecy leakage is one. Nowadays, I'm quite interested in injection attacks, right? Process scripting, arbitrary code injection, and so on. So basically, the attacker somehow managed to interact with the program in such a way that the program of their choice gets to execute, right? So this is an integrity problem. One way to do this is actually the reverse, or the same as your monitor, except I turn it into a tape tracking engine, right? So in your, let's say, in your monitoring scenario, you check the program, allow or abort. In the dynamic tape tracking system, this is okay, I keep going, I propagate taint. When I see that a untrusted input is used by an API that requires trusted input, I'm going to dump out the vulnerability report. Right? I'm going to say, hey, here's potential flow that could cause code injection, essentially. So, almost last slide. So this is, we've been working on Node.js. So JavaScript is a bad language. When I finished my PhD, I thought we're done with JavaScript, right? So that's what we thought. And then a couple of years ago, my collaborator said, hey, do you know that people are using JavaScript for everything now? Not just the web. It's called Node.js. So basically, one side of me is thinking it would be great if everything is Rust for assembly. On the other side, in reality, JavaScript is still one of the most popular languages out there. So I find it annoying. So it kind of wanted to keep me grounded to see actually what's really happening in the general developer field. Right? So here's code injection. So this is one convert function. It's probably API. It's actually trying to convert fonts for users. Except they take input a source. You see what's happening is that this source is concatenated with a bunch of other stuff and turned into command, and then eventually there's an exec. This command is actually executed, right? Now, if I call this API with this specific command, whatever the attacker wants would actually execute. Because Node.js code are mostly programming various applications, they can run on big servers dealing with customer data, so it's very likely they actually have high privilege, so it can be fairly bad. So this is like integrity violation, right? So this is what you're supposed to flow. This flow is the reverse of this. You have to take all the integrity data, get to API where it requires high integrity. So we have quite a bit of work going on there. I have to say it's not easier to find bugs than to actually make things more secure. So I think me and my students are having a bit of fun with that. Okay, so really the last slides. I do want to say where we are. So in terms of information flow types, the list goes on. Initially we have this Spark Ada, we have GIF. GIF actually in early 2000s, and Meyer's thesis. That's like the first significant work on information flow types. GIF is actually still alive and well, but when we try to ask our students to use it, everybody hates it. Then for JavaScript there's work, for OCaml there's work, Haskell there's work, WebAssembly there's work. Now people are doing Rust. There are a couple papers in the past couple of years about Rust information flow type system. And then I ran into OPLSS. I was complaining about this field has been 25 years, but it seems like there's still no real system. He told me that we should narrow your scope, find interesting narrow domain that information flow applies. And he picked hardware description language, very long stuff. And he said, it's great to work in that DSL and actually have impact. Right, so that's the landscape of type system analysis and so on. Monitor, the same thing. We build big systems. So in terms of OS, there are things like HiStar, Flume, there's other work. ICL4 actually has a difference. I think Yale, Zhongshan City calls also have some 9 different proofs on their system. People have implemented, so this is more of finding secrecy leak like Android on the Android OS. We have done work, instrument Chromium to ensure web applications being secure. And UCSD, Dion, Stefan has this cow, which is Firefox, our concurrent work. And Safari, at the same time, we have like Chrome, Firefox, WebKit. So we all know each other, but now the work actually ended up getting used. When we talked to the browser vendor, they were like 0.1% performance loss is a big thing. So every time they need to introduce security feature, they need to figure out how to optimize it to be within the error range, or they need to take out something else to allow for this performance loss of any features. Right? They're actually interested in thinking. We've been talking to them a little bit, but make it practical is really, really hard. Right? So that's where we are. Like we started in the late 70s, 80s. We keep going around this. We build systems, but the adoption is not. So there are fairly a lot of challenges, right? So usability is actually one of them. There isn't developer buy-in. They don't understand it. They don't know why they want to use it. So basically, yeah, I agree with Andrew. Maybe we end up scoping down a little bit, figure out what's the sweet spot, a application domain that actually easy to do. People have buy-in, actually make it work, right? Yeah. And also the specification-wise, we have, like for us, like for me, knowledge-based inference is great. The robust declaration is great, but you have to convey to the programmer why this specification actually work, why does it apply to our work. So that's a harder conversation to actually have. So that's what we are in the future. All right, any questions? All right, it's been a pleasure to actually teach you guys, and I will upload the slides, run the proof notes over Slack channel later today when I clean up the slides a little bit, fix all the bugs. Yeah. All right, we'll hang around if you have more questions. Thank you guys.